I welcome you all again. So we were looking into the Reynolds-averaged Navier-Stokes equations yesterday. Reynolds-averaged Navier-Stokes, or the so-called RANS equation. And we first took the continuity equation, right? So, and then upon Reynolds decomposition and averaging, we obtained two sets of equation, right? So we have for continuity RANS equation for incompressible flows. It is constant density. So continuity equation, we had three sets, or I used J, right? Dou Uj by dou Xj, that's the instantaneous version, and upon Reynolds decomposition and averaging, I got dou Uj bar by dou Xj equal to 0 for the mean continuity equation, right? And finally, we subtracted one from the other to get the continuity equation for the fluctuation. This is for the fluctuation. So three sets of equation and they look similar, so which is great. So upon averaging, but for the mean as well as for the fluctuation random component, they look similar. So we will see what happens to that in the momentum equation. So we look into the momentum equation. So let's write the instantaneous momentum equation first. So we have of the form dou ui by dou t plus uj dou ui by dou xj, the left hand side of the momentum equation or the acceleration terms, and steady and convective acceleration terms. And then we have the pressure gradient term 1 by rho dou p by dou xi plus, so we had this dou tau ij by dou xj, and then using the Newton's law of viscosity, we had this formula tau ij is set equal to 2 nu sij minus 2/3 mu skk. Okay. So this skk is nothing but dou uk by dou xk. So this goes to 0 in an incompressible flow here, right? So this term goes to 0 since dou uk by dou xk equal to 0. Continuity part. So only this term survives. So if I substitute this, so this is essentially 2 nu and then half of dou ui by dou xj plus dou uj by dou xi. So essentially I get two terms, and if I substitute here, I would get this last term here. This will be dou by dou xj of the first term, which is mu dou ui by dou xj plus dou by dou xj of mu dou uj by dou xi. Now what will happen to the last term here? Does it survive? See the last term here, we can differentiate this term first with respect to the j and then with respect to I. So the total, when we expand it, this term does not change. J and j are repeated indices. So I can first differentiate with respect to j. That means I can rewrite this as, I can say this is nothing but dou by dou xi of mu dou uj by dou xj. First differentiate with respect to j, then differentiate with respect to I, no problem, and therefore this is 0 again due to continuity. So only one of the term survives here. Okay, so only this term is surviving here. Right. So we have the equation, the instantaneous momentum equation. Now we apply Reynolds decomposition and average. Okay. So if I do this, Reynolds decompose and ensemble average. So Reynolds decomposition implies I need to now split, let's call this equation, what was the number? The last equation was 4, right? So we can call this equation 5. Which is missing? Oh yeah, so 1 by rho is missing, that is true. So I'll put here mu by rho is anyway constant. I can move in and out of the differential operator. Okay, so it essentially becomes kinematic viscosity now. Molecular viscosity divided by the density becomes kinematic viscosity. So Reynolds decomposition implies here for both ui and the pressure, both has to be decomposed into mean and fluctuation. So if I write now, equation 5 becomes dou by dou t of ui bar plus ui prime plus uj bar plus uj prime dou by dou xj of ui bar plus ui prime equal to minus 1 by rho dou p bar plus p prime by dou xi plus dou by dou xj of mu. So I can write mu here, kinematic viscosity, plus nu dou by dou xj of, or I can say dou square by dou xj ui bar plus ui prime. Okay, so now we essentially have to average the entire equation now, right? And averaging and addition, they commute, so it is separated out, as well as the differential operation here. So I need to essentially average the entire equation. So let me write this as dou ui bar by dou t plus so I get uj bar dou ui bar by dou xj plus uj bar dou ui prime by dou xj plus uj prime dou ui bar by dou xj plus uj prime dou ui prime by dou xj. It expands into 4 different terms, that is your convective or advective acceleration term, and the pressure gradient term into mean pressure gradient and fluctuating pressure gradient. plus and two different viscous stress terms, one for the mean, one for the fluctuation. Now we have to average. Ensemble average. So now the first term doesn't change anything. Ensemble averaging, the mean doesn't change anything to it. It has achieved its true mean characteristic. So ensemble averaging has no meaning here. So this will remain as it is. So I get dou I bar by dou t. This operation is unchanged. What happens to the second one? This is average of the fluctuation, right? So this goes to 0. So this term remains because this is already mean advection term. So I get uj bar dou ui bar by dou xj. Okay. Now we have few terms here. What will happen to the second term or the second term of this advection? Uj bar is the true mean, so it is like a constant, right? It can be taken outside the averaging operation, and therefore ensemble averaging of the fluctuation here is 0. So this term goes to 0. Same thing here, there is a mean strain, dou ui bar by dou xj is the mean strain or mean velocity gradient, which is a constant operator here. It has achieved its true mean, therefore it is outside the operation, you can take it out, and therefore its ensemble mean of uj prime is 0. What about this term? Yes, if you recall chapter 1 statistical analysis, that is the reason I started with statistical analysis, to introduce what is correlation. Correlation can go to 0, it can take a positive or a negative value, that is why I had this. So I have uj prime and then gradient of ui prime. We do not know what it is now, okay. At least we cannot say it is 0, we do not know, so we have to retain this term. So we retain this term, okay. I will move it to the other side of the equation later, because I want to write it in terms of equation 5, right. Equation 5 has, the way we write momentum equation is an unsteady acceleration, and then there is a convective term, and then right hand side we have some forces. So I would like to write in terms of that, and therefore I keep it like this. So on the right hand side I have this mean pressure gradient, which of course survives, and then this particular term, average of a pressure fluctuation is 0. That is why we needed the true mean concept. If you are working with arithmetic mean, we cannot achieve this equation, right. We are not doing any experiments, we are not doing any simulations. Just by assuming that true mean exists, we are able to achieve an equation for mean continuity, an equation for mean momentum, right. We are trying to get to some place without doing any experiments or simulation, right. For that, of course, we must believe that the true mean exists. So this is fine. So this term survives. So the viscous stress term, which is mu rho square ui bar by dou xj square. What about the last term? Average of the fluctuation, again goes to 0. Okay. So that means the one term from the left hand side, this is very important, I am moving the left hand side term to the right hand side. So this is minus of uj prime dou ui prime by dou xj average. Now if you compare, let us call this equation 6. If I now compare equation 5 and 6. This of course equation 5, this is gone, right. So if I compare equation 5 and equation 6, we see that this is not like what we expected coming from the continuity equation, the way we were being fooled by the continuity equation. Continuity equation, everything looks similar, right. The instantaneous, the continuity and the fluctuation all look similar, but not for the momentum. Momentum, you see the left hand side is fine, it is looking similar to equation 5 and 6. On the right hand side, the first two terms are also looking similar, right, the pressure gradient and the viscous stress term, but there is an additional term. So this is the sole additional term here. A new term has come up. This is a new term. So upon ensemble averaging the Navier-Stokes or the momentum equation, you get an additional term. So what is special about this additional term? If you look into the mean, we were interested in the mean flow like any engineer, but now you see if you want mean momentum, you must know about randomness also. You can compute for all these 4 terms, which is mean, but to get there we must have the knowledge of this last term, and only this last term knows about turbulence. Rest of the terms are all mean, statistical mean. It knows nothing about randomness. So this is the only term which knows about turbulence. Okay. Only term that knows about turbulence in equation 6. So we must have the knowledge of it before we can compute even the most basic information that engineers need. They would need pressure drag, they would need viscous drag, right. This is what engineers look for. Even to get there, we need this information, right. And another important aspect, what is the origin of this? So now we know that this is the turbulence term, right. So this particular term, it knows about turbulence as. So what is the origin of this term? So which term in the Navier-Stokes equation knows about turbulence? Exactly, the nonlinear term, right. So if you want to get rid of this term and then solve something, you know now that you cannot solve turbulence. The only term in the Navier-Stokes which knows about transition, turbulence, any other hydrodynamic thermal instabilities, everything is known by the nonlinear term. You cannot get rid of it assuming it is small, like if you follow some analytical methods, right. So this is the origin is from the left hand side. So this term originated from left hand side, that is nonlinear term or the advective or the advection or convection term. So turbulence is a non-linear process. So that term is very important. If you say this term is not important, that means your flow is laminar. You don't have any turbulence anymore, right? The equation falls back to a laminar flow. If these fluctuations are infinitesimally small, then you are essentially going back to a laminar flow, right? So if you are interested in turbulence, you must retain the nonlinear term. Okay, but retaining is easier, solving them is not easy. We will see, we will get there, what can be done to that one. So now I am going to do little bit of a trick here, because I would like to write this equation is fine the way it is, but I would like to write it in a different way so that you will appreciate the chapter 1 statistical analysis better. Okay. So for that I will make use of the continuity equations. So here, so this was equation number what was the, this was 4, this was 4, right, and this was 3 years, suppose, maybe, yeah, yes, this was 3 and this was 4, okay. So I will make use of this fluctuating continuity equation because it is 0, right. I can add or remove 0 from any equation, correct, without changing anything. So I would like to use equation 4 because it is essentially 0. So let us use equation 4. If I use equation 4, I have dou uj prime by dou xj equal to 0. Can I multiply anything to this term and it is still 0, right? I can multiply anything, right? So I would like to multiply this. So we can multiply this with anything and still it will be 0. Any other term and still it will be 0. So I would like to multiply this with ui prime, okay. So multiply with ui prime dou uj prime by dou xj equal to 0. It does not change, it is already 0, I can do whatever with it, right. So now it is already 0, if I take an ensemble average of a 0, what is it? 0, right. So ensemble mean of 0 is 0. So I am going to take ensemble mean of this term, that is I have ui prime dou uj prime by dou xj, I take ensemble mean here, it is still 0.